morning. Today we'll continue the crystal field theory with respect to octahedral complexes, and also we'll study calculation of crystal field stabilization energy, that is CFSE, with respect to octahedral complexes. So octahedral complexes means there are 6 ligands which are interacting with the metal ion, Okay, now according to CFT, okay, we'll discuss the formation of the complex. So now in the first stage, say the metal ion where the axes are passing through like this. Imagine the structure, and now the ligands are quite away from the metal ion. That means there is no interaction between the metal ion and the ligand. Very clear? So now then the 5d orbitals of the metal ion, they are at ground state and they are degenerate, means they are of equal energy. All the 5d orbitals are of equal energy. So now when the ligand field is approaching, say imagine it is surrounded the metal ion spherically. That means this field is created by the 6 ligands and which is surrounded the metal ion spherically, and it is symmetrically uniform, and also it is symmetrically uniform. So then what happens? At this stage, all the 5d orbitals are interacting with the ligand field, but all of them are at equal distance from the ligand field. Hence, they experience the same amount of repulsion, same extent of repulsion with the ligand sphere. As a result, the energy of all the 5d orbitals are raised with equal amount of energy. So thereby, say the energy of the 5d orbital is raised at this stage, okay, and still they remain degenerate, and this is only a hypothetical state. Now further, the ligand field which is spherically surrounded the metal ion is no more spherically surrounded. Now it is disrupted, or say distributed itself, okay, at a particular positions around the metal ion as shown in this figure. So two of them are concentrated along x-axis, other two along y-axis, and the other two along z-axis. That means after this the ligands are approaching the metal ion, okay, approaching the metal ion, and they are two of them are approaching the metal ion along the axis from both the sides, other two along y-axis from both the sides, and the remaining two along z-axis from both the sides. So you are well familiar the structure of d orbitals, all the 5 d orbitals, isn't it? Say the dxy, dyz, dzx, where the double dumbbell shape, where 4 lobes are oriented between the axis, and the fourth and fifth, say dx square minus y square and dz square, where the lobes are oriented along the axis. Now, so along the axis, the two orbitals are lying, dx square minus y square and dz square. So now the ligands are approaching along the axis, thereby these two orbitals out of 5, these two orbitals, they are experiencing greater repulsion when the ligand approaches quite nearer to the metal ion. So these two d orbitals are interacting, or say they experience, there is a head-on interacting, or they experience greater repulsion compared to the other three, dxy, dyz, dzx, which are lying in between the path of approaching ligands. As a result, there is a splitting of d orbitals. Okay, when the ligands are quite nearer to the metal ion, there is, due to interaction, there is a splitting of d orbitals into two sets. See, the one which contains these two orbitals, they are named as Eg orbitals, and the other three which are lowered by definite amount of energy, they are named as T2G orbitals. Okay, so delta O indicates it is the crystal field splitting energy. It is crystal field splitting, not stabilization. It is splitting energy. Okay, so now based on the splitting, that means strength of the field approaching ligand field, it may be higher value, it may be of lower value. Okay, so now say it is equal to taken as 10 dq, and in this case the 3 orbitals are lowered by minus 4 dq and the 2 orbitals are raised by plus 6 dq. Okay, so now even in this case also the same. So with this we'll go to the next calculation of crystal field theory. So crystal field stabilization energy. So before that, the central metal ion is the transition element which contains partially filled d orbitals. That means the metal ion may contain only one electron in its valence shell d orbital, or it may contain 2 electrons, 3 electrons, 4 electrons, any number up to maximum 10. So it is denoted by, say it is denoted by dx. Okay, say so now when the central metal ion contains dx number of electrons, okay, then the electronic configuration for dx number of electrons, the electronic configuration is T2g raised to P, Eg raised to Q. P is number of electrons in T2g orbitals here, and Q is number of electrons in Eg orbitals. Therefore, it is T2g raised to P, Eg raised to Q for dx system. Dx system means d orbital containing x number of electrons. X may be 1, 2, 3, 4 up to maximum 10. Is it? So now in this case, to calculate the crystal field stabilization energy, this is the formula: minus 4 dq into P plus 6 dq into Q plus n into P. So now this P indicates it is the pairing energy. It is the pairing energy. Okay. So while calculating crystal field stabilization energy, say the relation between delta 0 and P is important. So if it is a weak field ligand, then delta O is less than capital P. P is nothing but energy required to pair up the electrons. Okay. So if it is a strong field ligand, delta O is greater than P. So now during the calculation of crystal field stabilization energy, this should be remembered properly. So in case of weak field, this is the relation. In case of strong field, this will be the relation. Okay. So now imagine, say there are only one electron in the, say, d orbital of central metal ion. So when there is only one electron, okay, that electron according to Opper principle, okay, Opper principle says the electron always prefers to occupy lower energy level first. So when it is one electron, it always occupies this orbital, lower energy orbital. Therefore, the electron distribution or electronic configuration is T2g. That electron goes to T2g orbital and Eg orbital remains empty. Okay. So now, say P is 1 here, Q is 0. Therefore, the crystal field stabilization energy is minus 4 dq. Minus 4 dq. Okay, P is only 1. Clear? So now for D2 system, the second electron, suppose second electron is present, it goes to lower energy level. So from here it goes to lower energy level. Therefore, once again it is T2G2. There is no electrons in the upper orbital. Therefore, Eg remains 0. So two electrons are entering the T2G orbital. That means energy of the system or the metal is decreased by 2 into minus 4 dq. That means the energy say crystal field stabilization energy, it is calculated to be minus 8 dq. Suppose say the central metal ion is containing 3 electrons. So the 3 electrons, according to our principle, they prefers to here 3 electrons. So after this they will occupy this position. So that means D3. So here T2G 3. So all the say the T2G orbitals are like this. So the D1 it is D2, it is D3. Okay. So there is no electrons in EG orbital. So now once again P is 3 here, P is 3 here into minus 4, it is minus 12 dq. Okay. So now if it is now the central metal ion is containing 4 electrons in its d orbital. So now the question is, see the fourth electron, no doubt 3 electrons will occupy here only, and fourth electron, okay, where it goes, whether it occupies lower energy level or it goes to the higher energy level. Okay, so Hund's rule, they occupy singly first. Okay, so here they will occupy singly. Auger principle states that the electron always prefers to enter the lower energy level, and Hund's rule states that the pairing takes place only after all the available orbitals are singly occupied. Okay, now here all the 3 orbitals are singly occupied. Just now I have shown you. Say it is the, suppose here it is the, say T2G. So the D1, D2 and D3 is it. So now D4. So if the field strength is strong field, so here I have written strong field. Okay, strong field means this is greater. So then what happens? Say pairing is less, pairing energy is less, and going to the higher energy level is difficult because it is of long difference. That means large difference, energy difference is there. Therefore D4 goes to here itself. That means 1, 2, 3, the fourth will pair up here because delta O is greater than pairing energy. Okay, pairing is easy, so less amount of energy is utilized to pair up, but it is difficult to go to higher energy level. So thereby once again EG remains 0, and here say minus 16 dq. So now according to the formula there is one pair of electron is formed. So we have to show like this. Okay. Now D5 I am discussing it with respect to strong field energy, strong field ligand, and now the 5 it also enters the lower energy level. It goes to here. Fifth electron will pair up like this here. Okay, and T2G raised to 5, Eg is 0. So 5 electrons minus 4 into minus 4 dq into 5, it is 20 dq plus 2 pair. So okay, 2 of them are paired. Therefore now I have to show you like this. Okay, now D6 system. So now T2G, so one more possibility is there, one more electron can pair up. So D6 and Eg 0. The electron is difficult to go to the higher energy level, and it is easy to pair up here because pairing energy is less and delta O is greater. So thereby here it is 24 dq plus 3 pair of electrons are appearing. Okay. So now D7 system. Now with the D7 system. So now there is no space. Say here T2G orbitals. These are the T2G orbitals. So all are paired. All are completely filled. So therefore there is no other go. It has to go to the higher energy level. So D7 T2G raised to 6 and Eg raised to 1. Now how to calculate here? There are 6 electrons. Thereby it is minus 24 dq, okay, plus 6 into 1 it has appeared Eg. Therefore these are the electrons present in the Eg orbital. Therefore it is plus 6 dq into 1 it is. Okay, so thereby what happens here? Minus 24 dq plus 6 dq, it is minus 18 dq. Okay, here it is not minus, yes, minus 18 dq, and only 3 pair. Lower energy level, there are 3 pair of electrons are there. Now we'll go to the D8. So in a D8, say it is completely filled, T2G 6, and the 8th electron enters Eg orbital. Okay. So due to this, the decrease in energy is minus 24 dq. Okay. And increase in energy, so according to this formula, 6 into 2 plus 12 dq. So the total is minus 12. Therefore it is minus 12 dq, and there is no pairing in the upper level. There is pairing only in the lower level. Therefore there is 3p. Okay. And now the last but one, see if they contain, if the metal ion contains 9 electrons in this d orbital. So out of 9, those 9 electrons are distributed like this: T2G 6 and EG 3. So okay, now T2G 6 means P is 6 here, minus 24 dq, then 3, 6 into 3 is 18. So minus 6 dq plus, now the 3 electrons are entered here. There are only 2 orbitals, so 3 means 1 has to be paired. Therefore now the pairing is increased. And the last one, D10, so it is completely filled, T2G raised to 6, and EG also now it is completely filled, and 0 plus 5p. Okay, so this is the way of calculating crystal field stabilization energy in case of octahedral complexes with strong field ligand. So clear? So here, say once again, just I will wind up, say with few words. So metal ion and the ligands are quite away. The orbitals remain at the ground state, degenerate state, and when they are approaching the metal ion and when they surround the metal ion with spherical sphere in the form of spherical sphere, then all the 5 d orbitals are interacting with equal energy of repulsion, and thereby the energy of all the 5 d orbitals is raised, and this is hypothetical state, still remain degenerate. And further, when the ligands are no more spherically surrounded and they are concentrating at a particular positions around the metal ion, so say 2 of them on x-axis, other 2 y-axis, and other 3 z-axis, and thereby there is a head-on interacting between the metal orbitals of metal ion with the ligands. So those orbitals which are lying along the axis, they repel to the greater extent. So thereby the energy of those 2 orbitals are raised, and the rest 3 which experiences lesser repulsion, they are lowered by certain amount of energy. So the raising by plus 6 dq and lowering by minus 4 dq, and total is delta O, and that is equal to 10 dq. Okay. So now calculation of crystal field stabilization energy by using this formula. So one can write down the electronic configuration as T2G raised to P, EG raised to Q. Okay. And this is the electronic configuration for dx system. Dx means x stands for number of electrons present in the central metal ion. It may be 1, 2, 3 or up to maximum 10. So okay, and x is equal to p plus q. Those electrons are distributed among these orbitals in this way, p and q, small p, small q. And here the capital P stands for pairing energy. Okay, so now based on the strength of the approaching ligand field, if it is a strong field, delta O is greater than P. This distance is greater, therefore the electron, they will occupy lower energy in this case. That means D4th, D3 in both the case same distribution. But in the D4, from D4 there is a difference. In case of D4 here, the fourth electron present in D4, 4 electrons are present, and the fourth electron goes to here in case of strong field ligand. Similarly, D5, D6 and D7 and so on. Okay. So based on this equation, one can calculate the crystal field stabilization energy. Okay. So we'll continue in the next class.